Welcome to the Module 3 Graph Analysis. Now we talk about the centrality for hubs and authorities. And this probably is the most weirdest mathematical video that we have for you. But hang in there. We're talking about, as always, about the concepts so that you understand them. No one probably ever in the times of statistical software will ask you to do this stuff by hand that we're telling you. But I think it's really important to understand what is going on, why things are calculated in a specific way. So we probably dropped the word by accident a few times already, like authorities or hubs. So that's something you use in your daily conversation of graph theory when you hang out with friends on Friday evening, you don't know what to talk about, and you talk about a graph, and you're like, well, this is a great authority. And I'm like, but what is this authority actually? And authorities are really good sources in the graph, and hubs are good curators. And in an ideal graph, like not constant mathematically wise ideal graph, but in a functioning graph, that's probably a better word, good hubs point to good authorities and vice versa, so that those are connected to each other. And to understand the concepts of hub and authorities, we have to go back to out and in degree centrality. So out degree centrality measures how active a knot is. So it counts how many other knots connected to it. And so the example here is how many institutions does a bank lend money to. So how much they expose themselves credit risk-wise to other banks. Because not all the money is coming back. So a bank with a high out degree centrality is lending out a lot of money. It is really important in lending out. It connects to a lot of other knots from itself out. Vice versa, in degree centrality is, it measures how popular or trusted a knot is. So if everyone lends you money, everyone knows you actually pay that back. So this is the reverse aspect of the out degree centrality. As always, the wording is quite obvious. In degree and out degree centrality are related. But here we have the counts how many others connected to a specific knot. And when we talked about eigenvector centrality, there we measured a knot's importance based on the connections to other important knots. And in directed networks, we have to take into account this in degree and out degree centrality. Because here really this aspect of hubs and authorities matters. And this is the part where I'm like, okay, I tell you the math. I show you the math, but I'm not doing the math with you because we don't do the math anymore in times of computers. But so you have to know that the scores, it's an iterative process, and the scores are updated until they converge over time. And name dropping here, it's a HIT algorithm. So if you're really interested, hop over to your search engine and Google it. And it's quite similar to the eigenvector centrality, but now it considers a two-dimension. It differs between a hub and an authority. And if we calculate the hub and authority eigenvector centralities, we take the adjacency matrix of the directed network. And in the first step, we initialize the hub and the authority scores to a random number. And as always, the easiest number to use in math is 1. So we do this here with hj0, setting that 1 as the hub index, and the authority index aj0 also to 1. In the next step, we start the iterative procedure. We update for every score how many, or the authorities, the new authority score is we're counting all the other hub scores that are linking to it. So we add this up. We do the same for the hubs centrality. And in the third step, we normalize those aspects, all the values, so that they are, again, normally distributed, or add up to 1, that's the correct term. So that's the normalization aspect. And then we start again. We add up all the things that link to the authority or the hub. And over time, this number stops changing because it changes in the 5th, 10th, 20th digit. So there we have the convergence of the aspect. And then once we have the convergence, we have the hub and authority eigenvector centrality calculated. We do exactly the same with the cat's hub and authority centrality. And if you recall the cat's centrality measures earlier, we have this beta aspect, which gives a penalty for further distanced connections. And so if we do that, it's the same procedure with the Hitz algorithm that I just described for the eigenvector centrality for hubs and authorities, but here with this beta aspect, which also plays into account every other round. And we do the same thing. We update, we normalize, we start again, we update, we normalize until we have convergence. And we have here a really simple and easy graph just to show you how this can look like. We have 4 banks which are lending money to each other, and we have here on the bottom the hub eigenvector centrality, the authority eigenvector centrality of each bank. We have the cats and the hub cats and the authority cats are the same. And there we can see that considering the eigenvector centrality, the most important hub is bank 1. The most important authority is bank C. This relationship keeps the same with cat's centrality. However, the values are different. So you can't compare the concepts, and also the relationship between the banks changes. And that's the important aspect to keep in mind here, that this is the only thing that changes because of this beta parameter, which penalizes connections which are further away.